Our project was focused on equilibrium. Equilibrium is the state of a reaction where the concentrations of the reactants and products are equal at a constant temperature. Due to equilibrium, reactions can be either reactant or product favored depending on the three conditions listed on this slide. The favorable side of the reaction can be found by calculating the K value through the use of the equilibrium expression. That is, the concentrations of the products raised to their coefficients over the concentrations of the reactants raised to their coefficients. Remember that pure liquids and gases are not included when calculating the K value. If the K value is less than 1, the reaction is reactant favored at equilibrium, and is product favored if K is greater than 1. If the reaction is reversed, K can be found by taking the reciprocal of the original K value. If the reaction is multiplied, then K is raised to the number the equation was multiplied by. The equilibrium constant of pressure and concentration are not the same, but have relationship through this equation, where delta N is the number of moles of gas, R is the rate constant and T is the temperature in Kelvin. When the reaction is not at equilibrium, we can find the Q value, or reaction coefficient. This value is calculated the same way as K, but with non-equilibrium concentrations. Q and K can be compared to find where the reaction is in terms of equilibrium. If K is greater than Q, the reaction will proceed in the forward direction, if K is less than Q, the reverse direction. And if they are equal, the reaction has reached equilibrium. Le Chatelier's principle states that if a reactant or product is added to a system, the point of equilibrium will shift. All possible outcomes can be seen here. It is important to remember that increasing pressure will shift the reaction to the side with less moles of gas, and adding a catalyst will not shift the reaction, just increase its speed. Our lab demonstrates this principle.
First, we put 5 milliliters of the copper chloride solution into 2 test tubes. We set one aside to compare the color to. The other we put in a beaker of boiling water and awaited a change in color. After a short time, the solution turned green, indicating the shift in equilibrium. Then, we inserted the now green solution into a beaker of ice water. The solution then reverted back to its original blue shade. This concluded part 1 of the lab. To part 2, we again filled 2 test tubes with the solution and set one aside. Then we added 3 milliliters of the sodium chloride solution to the second test tube. This introduced more chlorine, increasing its concentration. This caused a shift in the reaction and caused the solution to turn slightly green. Then we added 3 milliliters of the silver nitrate solution, decreasing the concentration of chlorine and reverting the solution back to blue. This concluded the lab.